Welcome back, everybody. This is episode 29 of the Rule Your Pool podcast. I'm your host, Eric Knight with Orenda. I'm doing this solo today. We're doing it live, okay? One take, and we're going to talk about why we use so much acid in this industry, because now there's an acid shortage. This episode is about reducing acid consumption, and there is a difference between acid consumption and acid demand, but we're going to touch on things like why we should not be chasing pH, but instead we should be controlling it. So let's get into it. Episode 29, Rule Your Pool podcast. Welcome to Rule Your Pool, the podcast by Orenda that explains and simplifies pool chemistry so that anybody, regardless of experience, can understand it. I'm your host, Eric Knight, bringing clarity to these subjects so that you can bring clarity to your water. If you're ready to rule your pool, then let's go. First things first, we're in an acid shortage. Okay, COVID has led to supply chain issues up and down every single industry. Of course, we already talked about the chlorine shortage. Well, yeah, now it's an acid shortage too. So if you're having trouble getting acid, maybe not yet, but it could be happening. Hopefully they'll catch up. But I think it's a good time to address some bad habits that we have in this industry. Now, we have the program that we call the 6 Bad Habits, and it's really aimed towards the pool trade. And it's the top 6 money-wasting habits that they're pretty much free to change or very low cost, but people don't realize how much it's actually costing them. And the worst bad habit in terms of the number of problems that we see or the phone calls that we field have to do with abusing acid. Usually it's overdosing, dosing incorrectly in the first place, adding it improperly, like not diluting it, etc. The list goes on. In this episode, there is a difference here between the acid consumption that we actually use and the actual acid demand that the water needs. See, the demand is exactly what it sounds like, how much the water needs to consume. And it's very similar to the chlorine demand. Chlorine demand is, what does chlorine actually have to go against in order to maintain a free chlorine residual? The water effectively consumes chlorine. Okay, if we're putting it in layman's terms. Well, it does the same thing with acid, because acid is neutralizing alkali, and it's going to change, as we'll talk about pretty soon here with physics. pH is going to rise naturally. So every week you pretty much need to add some, unless you have trichlor as your primary chlorine, because trichlor is an acid. It's, I think, a 2.8 pH. So I have my handwritten notes here, my scribbles, quite a few things to talk about, and we're going to get through it very quickly here, or as quick and as cogent as I can. So let's talk about why we're consuming so much acid. The first thing is we have been conditioned by textbooks to chase pH. And when I say chase pH, I mean focus on pH parameters as if you cannot violate those pH parameters. And the reasons that the textbooks give for this is you have to have 7.2 to 7.8, or ideally 7.4 to 7.6. The reason they say that is for 2 reasons. One is bather comfort, which I can just debunk that right off the bat. I don't buy it. But the second one I do want to focus on, and that is the chlorine strength is affected by the pH. Now, let's expand on that a little bit. This is the second reason. The first one is we're chasing pH, and the second one is the strength of chlorine really matters. Well, on an indoor pool with no cyanuric acid, it does. The chart that we're very familiar with seeing is sort of an equilibrium between the strong killing form of chlorine, HOCl, hypochlorous acid. And when we think chlorine strength, we're really talking about the percentage of hypochlorous acid, percent HOCl. You'll see that if you read the Orenda blog, you'll actually see that term mentioned quite a bit, percent HOCl. The opposite of that, from a dissociation reaction, is hypochlorite ion, which is OCl minus. And it's got a free hydrogen ion because the hydrogen dissociated with it at a higher pH. Well, at about 7.5, it's roughly 50-50. Half of it's strong chlorine, half of it's weak. At 7.4, it's a higher percentage of strong chlorine. So the lower your pH goes, the stronger your chlorine. Again, without cyanuric acid. Look at our website, and in this video, we'll actually pop this chart up right now. Look at it now. Where's the red line when you introduce just 30 parts per million of CYA? Oh yeah, it's down there by the floor. And the reason is the vast majority of your chlorine is now bound to cyanuric acid. It's called a cyanurate, or an isocyanurate actually. And that molecule is no longer dictated by pH. HOCl is, or the percentage of it is. But now you've got a whole bunch of it that's bound to CYA, and it's a totally new chemistry. So what really matters to your chlorine strength is the free chlorine to cyanuric acid ratio, not the pH. I want to reiterate this. If you have cyanuric acid in your pool, the pH is not controlling the strength of your chlorine in any meaningful way. In a negligible way, it has some impact, but it's really not noticeable. And some chemists may be really, really particular about how I word that, but in effect, you're not going to notice the difference, okay? It's the free chlorine to cyanuric acid ratio that matters now. So why are we trying to maintain a 7.4 to 7.6 pH, if that's the case, in an outdoor pool? Of course, in an indoor pool, yeah, I get it. There's no cyanuric acid. You got to make sure you have strong chlorine. But in an outdoor pool with cyanuric acid, I don't think you really need to be thinking about pH for chlorine strength. And as I already, without going into it, maybe it'll be a future episode, the bather comfort thing, I don't buy it. I was a swimmer. I've got my 10,000 hours. I don't buy it at all. I drink spring water and bottled water that's 9.5 pH from some brands and 6 pH from others. I don't really taste that much of a difference, and it doesn't irritate me either way. So that's a much bigger range than we're going to have in swimming pools. So I don't buy the pH argument. I do think it's chloramine byproducts and oxidants and things like sunscreen that get in our eyes. That irritates bathers, but it's not the pH specifically. So the third thing of why we use so much acid, first one being we're trying to chase pH. The second one being a reason we're chasing pH, which is chlorine strength, which I think is misguided if we have cyanuric acid. The third thing is with plaster pools especially, if there's ever an issue, acid seems to be like one of the first things that people turn to, especially on a startup or in, plaster companies or anything like that. If there's an issue, modeling, discoloration, scale, hit it with acid. Oh, you got some streak lines? Hit it with more acid. Oh, you got a puddle mark there? Hit it with a lot more acid. Is that really the answer? I think it should be one of the last resorts, not one of the first. Now, balancing the LSI is going to be the key to handling calcium issues, because what if you don't have scale? What if it's crystals? What if it's winter dust? Right? What if it's plaster dust? If you don't know the source of the problem, if you don't know your actual LSI chemistry and can work backwards for how those marks were actually caused, why would you just go to a prescription without a proper diagnosis? You're like pouring rubbing alcohol on the fire because it looks like water, but it's just going to make the fire burn hotter, right? So you don't want to do that necessarily. You want to figure out what the actual problem is. So the first resort would be test the chemistry and adjust the LSI. And yeah, that may take some acid, some diluted acid, correct the pH or the alkalinity, but that's way different, huge difference between that and using acid as a remedy by dumping it into the pool to clean things up. So keep that in mind. So those are I think the three reasons for the high acid consumption. There's probably other reasons too. Like we'll make mention of it a little bit later, but we have to have 16 ounces of acid for every gallon of liquid chlorine to neutralize the chlorine. That's not really true because temporarily you want to take the edge off, sure, but you don't need 16 ounces. We've had a lot of success with 4. Some people like 8 ounces. You don't need 16 because the chlorine itself, after it oxidizes and kills, releases its own hydrochloric acid and it neutralizes itself. Almost a perfect wash. Not quite, but for all effects and purposes, liquid chlorine and cal hypo have a temporary pH rise. They will bring themselves back down, okay, after they do their job. So that's, again, a result of some bad habits. And if you look at the textbooks, they actually mention this. Just people just don't process it, I guess. So you just want to take the little bit of the edge off so that it doesn't cloud up your pool. You want to lower the pH a little bit before you add cal hypo so it doesn't turn your pool white for 20 minutes. And there's some validity to that, but you don't need 16 ounces per gallon of liquid chlorine. So the way we're going to reduce acid consumption is just by being more mindful of what we're using acid for. Is acid really what we need to do? And let's look at it through the context of the LSI, not ranges. If we're just focused on range chemistry, well, yeah, you got to be 7.4 to 7.6 or 7.2 to 7.8 or whatever. I need a lower pH. I have to have that. Do you? I mean, are you treating your pool right now in July the same way that you are going to be treating it in October? Or during the winter? Or in the spring when you open it up and it's 50 degrees, not 90? Are you really thinking about temperature and other factors that change throughout the year? Or are you just following the textbook because it says you have to have a 7.4 to 7.6 ideal pH? That's what most people do. They just follow the textbook ranges, and it leads them to problems because you're not thinking about the LSI. The LSI has to come first. It is the first priority. So what I want to introduce is this concept of containing pH instead of trying to control it. pH doesn't want to be controlled. It cannot be controlled because it is in equilibrium, number one, so it can change very quickly. But the other thing is it's a reactionary chemistry. Anything you do to the water, the pH is going to react. It's going to change. All right, it's going to move around. Bathers jump in, pH moves a little bit. Bather pees in the pool, pH moves a little bit. You add literally any chemical, pH changes. All right, so it's a reactionary thing. You're not going to nail this thing down. And yet pH is extremely important. You look at the LSI, a fluctuation of pH makes a big difference on the LSI. So why are we trying to nail it down if it's always evading us? Can you maintain a pH for 10 minutes? I can't. And that's because we're fighting physics. pH isn't meant to be nailed down. All right, and you're going to lose that battle eventually. And the only way you can really, quote unquote, I'm using air quotes, control it is with a controller. And what does a controller do? Well, it just feeds acid all the time. And it feeds acid usually on something called a sense and dispense system, where it's kind of like a thermostat in your house. It just cools the air until the thermometer says it's cold enough, and then it stops cooling. Well, it's the same thing with acid. It just feeds acid until the pH probe says, okay, the pH is going back down into range. Cool. Yeah, but there's a lot of time in between when you start that acid feeder and when the probe reads a change in pH. And what happens is these chemical controllers, they chronically overfeed acid. And I'll explain an alternative towards the end of this episode for that. But you can avoid the sense and dispense pattern, and it'll save you a ton on acid, especially if you're a commercial operator or a high-end pool with chemical automation. You may not realize how much acid you're consuming that you just simply don't have to consume. So again, I'm following my notes here because I don't have anybody to do this with. Joe is in California. Harold was traveling. Jared's too busy. You just get me. And so since I don't have somebody to bounce off of in this episode, I'm bouncing off of my piece of paper. Bear with me. All right. Because we're trying to control physics, I have this rubber band in my hand, and you on video can see this, but I just have a rubber band hanging on my finger. When you make a pH correction, if you go too far away from where water wants to be, it's going to put stress on that rubber band, and it's going to pull you back to where water wants to be. The further you stray from equilibrium, the harder it pulls back. The closer you stay to equilibrium, you actually might be within the slack of that rubber band, and the pH doesn't have any incentive to move. And it's similar to the LSI. If 0.0 is where my finger is, and that's equilibrium for the water, if you go too low, the water's going to correct itself back up. If you go too high, the water's going to precipitate scale, and it's going to drop itself back into LSI range. Water only seeks one thing: equilibrium. That's it. That's all it wants. It doesn't want to ruin your day. It doesn't want to cost you more money. It doesn't want to be dirty. It doesn't want to be cloudy. It wants equilibrium. And there's a whole bunch of different equilibrium that it wants. For instance, LSI balance is the objective measurement of what water balance is. Calcium carbonate saturation. Water really wants that. It wants to be balanced on the LSI. But there's other things that want to be in equilibrium too that affect water. Not water itself, but they affect water. And that's really the crux of this episode. And it's carbon dioxide. And we're going to explain that this is a law of physics. And if you're trying to control pH, you're violating this law because you're trying to follow the textbook. But the textbook is basically telling us where pH would ideally be for chlorine strength and quote unquote bather comfort, whoever decided that. I don't know who wrote that, but I don't agree with it. Either way, that textbook is basically telling you how and where to force water to comply to your will. Well, I got news for you. Physics doesn't care about that textbook. It doesn't care about your opinion. It doesn't care how long you've been treating pools. Physics is physics. And this that I'm about to explain is a law of physics, not a suggestion. And we have to embrace this because if we don't, we're going to be fighting against it and you're eventually going to lose. And you probably actually already are. And you're going to realize when I explain this, you're going to probably think like, oh my God, that makes perfect sense. Yeah, that's why I've been fighting it. Makes sense now. And I hope you have that epiphany, because I know I did. And everybody that we talk to in classes, they're kind of blown away by this, because we never really thought about it from the perspective of who is listening to what water wants. We're trying to force water to do something. Shouldn't we pay attention to where water wants to be and then try to accommodate around that? That's what this is. If you're going to write something down, this is called Henry's Law. Henry's Law of the solubility of gases, Henry's Law of differential pressures. There's a few different names. The law itself kind of encompasses a whole bunch of things, so I'm just going to call it Henry's Law. Essentially, Henry's Law came out in 1803, and he said that any gas dissolved in a liquid is going to equalize with a proportional partial pressure of that same gas above the liquid. So if you got water, any gas dissolved in that water has to be the exact proportionate pressure of that same gas above the water. All right? And it's not necessarily equal, it's proportionate. So in this case, the gas we really care about is carbon dioxide. Why CO2? Because the amount of CO2 is going to help us determine the pH. Technically, pH is the concentration of hydrogen ions, but CO2 is directly interacted with that with carbonic acid, and we've got plenty of articles about it. That's a rabbit hole. The point is, CO2 is going to determine the pH in terms of not literally, but effectively. That's a good way to think about it. The less CO2 in your water, the higher your pH. The more CO2 dissolved in your water, the lower your pH, because you'll have more carbonic acid. That means you have lower pH. So if you think about this in practical terms, if you have waterfalls, spray features, splash features, vanishing edge, aeration of any kind, bubbles, whatever, your pH rises in those pools pretty quickly. The reason for that is those bubbles accelerate the loss of CO2. Your CO2 leaves, your pH goes up. Conversely, if you want to reduce pH, you can inject CO2. The pH goes down, but the alkalinity doesn't. And the reason the alkalinity doesn't is because you didn't do anything to the alkalinity. You just introduced more carbonic acid. Carbonic acid is dissolved CO2. Now, acid reduces pH, but where does acid get the CO2? If you need more CO2 to lower your pH, how does HCl find a CO2? Well, it takes it from alkalinity. The way I describe it, it's not chemically accurate, but it's a good visual, is it burns through alkalinity. Acid will burn through alkalinity, extract the CO2, convert it to carbonic acid, and boom, your pH goes down. So you go and you consume alkalinity with acid to reduce your pH. That's why they both go down. Alkalinity and pH get reduced when you put acid in the pool. But CO2 bypasses the alkalinity, doesn't care about that. It just directly creates carbonic acid. We have mechanisms to reduce our pH, acid and carbon dioxide. But Henry's Law is really about the concentration of CO2. Henry's Law is generally any liquid, any gas. But in our case, it's the concentration of CO2. I can shortcut to the end and say pH has to naturally rise up until the CO2 is in equilibrium with the air above the pool. That's what's going to happen. And I say it's going to happen because it's going to happen. It's physics. It has to. Now, you can suppress this, like using trichlorochlorine, which will suppress the pH because it's acidic, but it's also going to chew through your alkalinity to do that. Okay, you can't do it forever. Here's a good analogy to think of. This is what helps me visualize Henry's Law. Think of a bottle of beer. When it's sealed, there's no bubbles in the beer, but you crack it open, and CO2 escapes. That's where the pressure came from. And suddenly, in the middle of that beer, bubbles appear out of nowhere. And what you're looking at is Henry's Law in action. That beer was carbonated. It had a lot more CO2 in it than flat water. That's what makes it fizzy. Same with a soda if you don't like beer. And so when you opened it, suddenly it's no longer in equilibrium with this pressurized pocket of air right under the lid at the top of the bottle. Now it has to equalize with the room, or if you're drinking outside, the atmosphere. Well, there's a lot less pressure of CO2 in that room compared to that bottle. And so now you have this furious surge of CO2 leaving the drink so that it can equalize with the room. That's Henry's Law. Now, the exact same physics is happening in a swimming pool. We just don't see it. You think of the surface area of a bottle, the whole of a bottle, 3/4 of an inch maybe, compared to a swimming pool. Now, so you have an infinitely larger surface area, and you don't have nearly as much carbonation. We're not swimming in frizzante water. We're swimming in carbonated water that has like bicarbonates and carbonate alkalinity. All right, so you do have a lot of carbonates, and technically it is overcarbonated, but that's how we stabilize our water. So that has to equalize with the atmosphere, and that's why the pH rises. You're not doing anything wrong if it rises. It's supposed to rise. Let it rise. Because it can only rise so much until it reaches equilibrium. When it gets to equilibrium and the CO2 is balanced with the air, you reach something that Orenda calls the pH ceiling. When you get to that ceiling, your pH cannot rise naturally any higher. And that's a really good thing. It has to stop, because eventually, if you get to that ceiling and something forces your pH to go any higher, the atmosphere will literally push CO2 back into your water. That's the other side of Henry's law. Equilibrium is where water wants to be. It doesn't want to get greedy. So pH can be forced over it. Like if you etch cement and you get calcium hydroxide with a 12.6 pH, oh yeah, you can definitely have a higher pH. Or the temporary pH spike of liquid chlorine or something up until it corrects itself. Yeah, the pH can be higher. Salt systems, sodium hydroxide, pH can be higher. But by and large, the pH ceiling is something that is going to be the limit. And if we do our job right, you're never actually going to hit it, because as CO2 gets closer and closer to equilibrium, again, Henry's law, it slows down in a sort of a square root rate. In other words, it gets exponentially slower to off-gas the closer it gets to equilibrium. And that's really good for us too, because if we know where our pH ceiling is, let's say it's 8.2, and there's a chart on our website on several of these articles, and you can look up your temperature at 80 degrees, 50 carbonate alkalinity is like 8.13. 60 carbonate alkalinity is going to be 8.20. So let's just say it's 8.2. I'm not sure you're ever going to get to 8.2, because you're exponentially rising slower and slower and slower the closer you get to it. So after a week, let's say it takes, I'm making up these numbers, but let's say it takes a minute for the pH to go from 7.2 to 7.3. Okay? Well, by the time you get to like 8 or 7.9 to 8.0, it could be days. All right? We're talking exponential here. So it could be days to get there. And so if you're coming once a week, or you're treating a pool twice a week if you're a homeowner, don't do it more than that. That's helicopter parenting. Don't do it more than that. If you're not treating the water every single day, the pH is never really going to get to its ceiling, assuming you show up once a week. Now, if you neglect it for a month, it probably will. But realistically, it can only go so high, and it's exponentially slower and slower and slower the closer it gets to 8.2. Embrace this. Use this to your advantage. So this is the containment strategy that I really want to talk about. I want you to think of this pH ceiling, which you can control. You can determine how high it is based on your carbonate alkalinity. Okay, not your total, but your carbonate alkalinity, which is total minus a third of your CYA. And if people use borate contributes to this. It reduces your carbonate alkalinity because you have to deduct borate from it as well. So this is why it helps. It helps fight against pH rise. This is exactly why that does that, because it lowers the pH ceiling effectively. And then you get the benefit of the exponential slowdown at a lower ceiling. So if you have less alkalinity in your pool, you're going to have a lower pH ceiling. Kind of cool. This is why Orenda teaches, if you have a salt pool in the summertime, you don't want over 80 alkalinity. You probably want more like 60 or 70, maybe even 50 if you're really good. Now, I don't want to be misunderstood. I'm not condoning you just throw out these low alkalinity numbers, because there's some responsibilities you have if you're going to do that. You have to have enough calcium hardness to offset the LSI deficit that you just created by reducing your alkalinity. You need more calcium than you might think. The second thing is, when you make that correction or a pH correction at lower alkalinity, you better look at the dose. Because if you had 100 alkalinity and you dropped it down to 60, you now need 60% of your acid dose that you had at 100. Okay, it's directly proportional. So, if you are used to putting in a quart of acid every week and you cut your alkalinity in half, well, your dose just got cut in half. So use the Orenda app. It'll dose properly, but you're going to want to test your alkalinity every time. So there are some responsibilities. You can't just have low alkalinity and expect, oh, well, Orenda told us to do that. No, I didn't. What I did say is you can reduce your pH ceiling. I didn't say you have to. I just said you can. And I would recommend, certainly for salt pools, cal hypo, and liquid chlorine pools, that you go a little bit below 80 in the summer, but not in the winter. When the water is cold, you need more alkalinity. You need a higher pH ceiling. You need this insulation so that you're not damaging your pool. If we think of this ceiling as the ceiling in a room, and their pH is going to start at the floor each week because you're going to reset it, and it's just going to rise up, and it's going to get slower and slower and slower the closer it gets to the ceiling. That's a pretty good visual. But that's what I was teaching for a while. But I think a better analogy is an elevator, okay? A lift. You walk in there, there's a ceiling, there's a floor, and the whole room changes throughout the season based on water temperature because your LSI parameters change when the water temperature drops. You need more calcium, you need a little more alkalinity, you need a little higher pH ceiling when it's 40-degree water, Fahrenheit, versus 90-degree water in the summer. Big difference there. Now, the containment strategy is identical, but your parameters to match it on the LSI change because the water temperature changed. So that's why it's an elevator instead of just a room. So let's look at the floor now. What is the LSI floor? Well, we have to have enough insulation of LSI with calcium hardness to accommodate for that lower alkalinity so that when we correct our pH, we're going to drop our LSI as low into the yellow on the Orenda app as you can without going red. If you go red, you break through the floor. All bets are off. But if you go yellow and you allow that pH to rise throughout the week, it's not going to be yellow very long, okay? Because it's faster to rise in the early stages and exponentially slower at the higher stages. So it's not going to be yellow for more than maybe a day. And yellow is still technically okay. It's not etching. It's not damaging. The pH is going to rise. And it's going to pull you into the green, and you're going to be green all week pretty much. That's a great containment strategy. So now you know what your floor is. Usually, 9 times out of 10, it's going to be 7.5 or 7.6. I've never seen it 7.4 in practical reasons unless you had really hot water. But realistically, you're going down to 7.5 or 7.6. On a salt pool, it's probably 7.6. Just because you're going to have less alkalinity in a salt pool. But the point is, you're going to reset your pH to say 7.5 or 7.6, whatever the calculator allows you to do, given your parameters. And it's going to rise naturally and exponentially get slower closer to the ceiling. And then you come back after a week, and you just reset it. Do it again. Make sure that when you do it, you're testing your alkalinity, because eventually you're going to whittle down that alkalinity. Maybe you start at 70 and then you got 65, or eventually 2 weeks later, maybe you have 60. Okay, reset it to 70. Now that's a micro adjustment. That's not a lot of sodium bicarb. Contrast this strategy, which we're doing micro adjustments here, to what we've been doing traditionally in this industry, which is chasing pH and therefore chasing alkalinity because it's this dance. Oh, I have to have a 7.2 pH. Do you? Yeah, I don't buy it anymore. I don't think you do, because you're using too much acid to get there, and you're probably not dosing it right because most people just eyeball it anyway. And if you use too much acid and you take out more alkalinity than you intended, well, that is a self-fulfilling prophecy. This builds on itself, and now you need to put more bicarb in, and then you have too much alkalinity, which raises your pH ceiling, and now your pH goes higher than it was supposed to, and then you get scale, and then you get all this other stuff, and you can see how this gets exhausting. I'm hoping that some of you listening are resonating with what I'm telling you, because you've probably been here. If you've been operating your pool for more than a year, there's a good chance you know exactly what I'm talking about. It's physics. It's not an opinion. This will continue to happen to you unless you think differently. So I look at this acid shortage, kind of like I look at the trichlor shortage, and I say, what a great opportunity. In the short term, yeah, it sucks. It's kind of a crisis for a lot of people. But what a great opportunity to think differently and start reducing our acid consumption. Containing pH will not only reduce our acid consumption, it'll reduce our acid demand. The difference, I think I mentioned it earlier, at least I hope I did. The difference is the acid demand is what water actually needs, and the acid consumption is what we actually use. Hopefully they should be exactly the same. there shouldn't be much of a difference at all. So that's the containment thing. There's a few other items that I would like to cover here, and a few ways to save acid in other ways. So number one, always dilute it. Number two, always measure it. Okay, know your dose. Measure the pool volume so you have your dosage correct. That's very, very important. Otherwise, you might be adding too much and not even know it. If you don't dilute it, it's going to punch to the bottom, it's going to etch, and then it's going to neutralize the acid, and it doesn't actually do the full correction that it was supposed to do, and it could cause pool damage. The other thing is know your tap water chemistry. Maybe if you have really low alkalinity out of the tap, acid is not the best option for you. Maybe that pool should be on a CO2 system. Inject CO2 because it doesn't have a lot of tap water alkalinity. And maybe that's not the case either. Maybe a little mixture of both. Some commercial pools do both. When the alkalinity gets too high, it switches to acid, and then it goes back to CO2 when the alkalinity gets down. If you have chemical automation, especially on a commercial pool, it's probably worth an extra conversation. You might just want to request a training with us because that's a much longer conversation to abandon the sense and dispense and get to a prescribed amount of acid every week. But one thing you can do in the short term is turn your feed pump to the slowest setting possible to maximize dilution. A lot of these commercial pools are pumping 800 some gallons a minute or more. And the slower you can pump acid into that rushing line of plumbing, the better, the more diluted it will be. And I think I mentioned earlier, you want to change that habit and reduce the amount of muriatic acid per gallon of liquid chlorine or cal hypo. You don't really need as much as you need. You just try to take the edge off so it doesn't cloud the water in that moment. But the chlorine itself is going to neutralize itself after it does its job. And then finally, stop using acid as a first option when it comes to a plaster discoloration. Look at the LSI first, figure out what the actual problem is. Feel free to reach out with us. We look at these issues all the time. And I say all the time, literally like every day, people call us with issues. So we do know what we're looking for, and we will be happy to help you out. So I think that wraps it up. Let's not only reduce our acid consumption, but our acid demand by containing pH instead of chasing it, i.e. controlling it, because pH is never going to be controlled. You'd have to fight physics to do that, and good luck with that. I'm Eric Knight with Orenda. This has been episode 29. I hope you were able to deal with some of my ADD. I did the best I could. Hopefully I'll have somebody on the next episode, and I don't even know what we're going to talk about, but I hope that you found this valuable and that every episode that we do is relevant to you in some form or fashion. If you know somebody who needs to hear this, maybe you have a friend with a pool and they're probably using too much acid, or most of us are, let's be honest. There's no shame in it. This is changing a habit, okay? I'm not judging anybody for doing this because none of us know what we don't know. A year ago, I didn't know any of this. Well, actually, that's not true. 2 years ago, yeah, that's right, pre-COVID. 2 years ago, I didn't know any of this. So, and yet I was still teaching water chemistry. So we learn as we go. And I don't know any of this information. Feel free, look at our website, and we cite out to a whole bunch of sources. Just do an online search of Henry's Law, and there's some great materials online on YouTube that explain it better than I can. Just know that it's happening. It's happening in your pool. And we have to embrace that, or we're going to have to fight it. That's your decision. Thanks so much for your time, everybody.
Thank you for listening to Rule Your Pool, a podcast by Orenda Technologies. For more information on what we discussed in this week's episode, check the links in the description or visit www.orendatech.com.
I hope you find this show valuable enough that you tap that subscribe button and share it with your friends. You can also like us on Facebook and social media. And with our help, you'll be able to rule your pool without over-treating it with chemicals and wasting money. I'll see you next episode.